We'll talk about individual fats in a minute because obviously mitochondria like certain fats and not others. We're going to talk about that in a minute. Okay. But fructose is a dose-dependent mitochondrial toxin, and it's the thing that's been going up 250 to 2,500%.
And I want to pause here and give you a chance to unpack that because we've talked about it before, but also there's a lot of chatter online and some people take issue with this. So can you just define precisely dose-dependent mitochondrial toxin and emphasize very clearly, if you can, the dose-dependent part of it?
So it's dose-dependent like alcohol, okay? Alcohol is dose-dependent as well. Bottom line, fructose has calories, 4.2 calories per gram. Yeah, I know. They do. That's only if you burn them to ATP. What if you don't burn them to ATP? What if actually fructose stopped burning? Well, in fact, it actually does that. How does it do that? Well, a metabolite of fructose, which I mentioned earlier, called dihydroxyacetone phosphate, DHAP, in the liver, okay, where it's being metabolized. So fructose goes to fructose 1-phosphate and then ultimately gets cleaved to glyceraldehyde 3-phosphate one direction and dihydroxyacetone phosphate the other direction. That dihydroxyacetone phosphate has the opportunity to become a compound called methylglyoxal, MgO. Methylglyoxal. And methylglyoxal has an Al at the end, which means it's an aldehyde. Okay, so everything that's an aldehyde has an Al at the end. Methylglyoxal has an aldehyde. That aldehyde, and it's now a 3-carbon fragment, methylglyoxal, has an aldehyde, and it fits right in the active site of the gamma subunit of AMP kinase.
So that's one of the 3 major pathways we talked about, which regulates whether or not a cell is going to be in growth versus burn mode.
Exactly right. And that AMP kinase determines whether or not you're going to build new mitochondria. Well, this aldehyde, this methylglyoxal, insinuates itself right into that gamma subunit where the AMP should be in order to generate a increase in activity and therefore an increase in number of mitochondria.
Right. So if you mess with that,
which
you would do by having too much fructose around, you won't make as many mitochondria, and therefore you won't be able to handle as much glucose, and therefore it'll be left over to make fat.
Number one. And number two, that enzyme that it bound into the gamma subunit, that aldehyde will react with one of the 3 arginines in that active site and will form a covalent bond, okay, just like the Amadori rearrangement. Basically, now that methylglyoxal can't come out of that active site.
You just broke the little machine.
You broke the machine, right? It's irreversible inhibition. It's called in biochemistry. Irreversible inhibition. Okay, you've killed that enzyme, and then you have to make a new enzyme.
Right.
Except you're not going to make a new enzyme because you turned the friggin' thing off.
Yeah, you're having an energy production problem, and there's always a trade-off. There's only so much energy to do so many things. If you've got to make a new enzyme because you broke it, well, you need to be able to make it. You might not be able to do that. But even if you could, that energy would have gone to something else. And there's a lot it could have gone to in a developing fetus.
Exactly. What's going to happen now to that, to the energy that was being poured down that glycolytic pathway to hopefully get to pyruvate in order to be able to enter the mitochondria, which is now friggin' broken? Well, there's only one thing that can happen.